Three numbers. 1, 2, 2. How many subsets add up to exactly 3? Take a second. The answer is not as obvious as it looks. It's the same state we've seen before, index and target. But with one tiny change to a single operator, the question transforms completely. And there's a sticky edge case hiding in plain sight that trips up almost everyone. Here's the problem. You're given an array of non-negative integers and a target k. Count the number of subsets whose sum equals exactly k. Let's work on example. The array is 1, 2, 2, 3, and k equals 3. Watch carefully. 1 plus 2 gives us 3. But there are two different 2's, so that's two distinct subsets. And the 3 all by itself makes a third. So the answer is 3 ways. Counting, not just checking. So how do we count? We use the same state as subset sum. F of I and t is the number of subsets, using the first I elements that sum to t. At every element we make a choice. Skip it or take. Here's the key insight. In the feasibility version, we combine those choices with or. Can we do it this way or that way? But to count, we don't ask yes or no. We add the number of ways without this element plus the number of ways with it. Swap over for plus, and feasibility becomes counting. Now for the center mark, the zeros. Here's why they're so tricky. A zero adds nothing to the sum, so it can be inside a subset or outside, and the total never changes. Which means every zero doubles your count. Take the subset that sums to k. Now you can include the zero or exclude it. Two valid subsets, same sum. Each zero multiplies the possibilities by 2. This breaks the naive base case. You can't just say there's one way to reach 0. So we handle the first element carefully. If the first element is a 0 and the target is 0, there are two ways: the empty set and the set containing that 0. Otherwise, one way for an empty target and one way if the element equals the target. Zeros at later positions take care of themselves, because take and not take both read the same cell, doubling it automatically. Let's put it together in code. The tabulation approach. First, the base row. If the first element is a 0, dpf 0 gets 2, otherwise it gets 1. And if that first element is positive and within k, we mark its position with a single way. Then we fill the table. For every element and every target, not take carries down the count from above. Take pulls from the column shifted by the element's value. We add them together. That's it. The answer sits in the bottom right corner. Watch the table fill. Each cell accumulates counts, not just yes or no. And when a 0 element appears, watch its entire column double right before your eyes. One more refinement. Notice each row only ever looks at the row directly above it. So we don't need the whole table. We collapse it into a single row, rolling it forward as we go. Space drops dramatically. Let's talk complexity. Time is order n times k. Space, after optimization, is just order k. And a warning, these counts can grow huge, so use a 64-bit integer. Or take the answer modulo 1,000,000,007, as many versions require. Two pitfalls to remember. First, mishandling zeros. This is the single most common bug in the entire problem. Second, integer overflow on the counts. Guard it in sport. Here's the big takeaway. Swap the combine operator and you change the question itself. OR gives you feasibility. Plus gives you counting. Min or max gives you optimization. But the state stays exactly the same. Master one and you've mastered them all. Next, we'll use this counter as a building block to count partitions whose two halves differ by a fixed amount. Practice the zero doubling until it's second nature. See you in the next one.